Hi there, we're going to take a look at rectangular coordinates, and in particular we're going to look at distance and change. Change is a directed distance, so distance plus direction. So here we have an x-axis, which we will label as an x-axis, and we have two numbers plotted. If we want to find the distance between 3 and 8, we can count the number of spaces and see that it is 5. Now the direction doesn't really matter here, so the distance between 8 and 3 is also 5 spaces. The direction does start to matter when we look at change. So when we talk about the change from 3 to 8, we have an increase, and that change is a positive 5. So an increase of 5 from 3 to 8 means that the change is positive 5. Now if we go in the opposite direction, if we start at 8 and we want to find the change from 8 to 3, that change is negative 5, which means a decrease of 5 from 8 to 3. So here we see that direction matters when we calculate change, but it doesn't matter when we calculate distance. In general then, we say that change is the final value minus the initial value. The change in x we call delta x. Delta is a Greek letter that means d and stands for difference, the answer when we subtract. We can also calculate delta y. We take the final value minus the initial. So to go from A to B, we start at A, which is the initial value, and we end at B, the final value. And so the change from A to B is the final value minus the initial value. And that works out to be B minus A. And the change from B to A is A minus B. It's a little bit backwards from what we think, so we have to kind of remember final minus initial in each of these expressions. When we want to calculate distance, we know that the distance between 3 and 8 is the same as the distance between 8 and 3. And so we say that distance is the absolute value of change. So we calculate our change, but then we use the absolute value, which ignores the negative signs because, well, distance can't be negative. So the change from 3 to 8 is positive 5, but the distance between 3 and 8 is the absolute value of positive 5, or just 5. And similarly, the change of negative 5 has a distance which is just 5, because the absolute value ignores the negative sign. And so our distance of 5 is the same whether we go from 3 to 8 or 8 to 3 in calculating distance. Absolute value ignores the negative sign. So in number 4, we see that the distance between A and B can be expressed as either the absolute value of A minus B or the absolute value of B minus A, because those two expressions are the same. The order of subtraction doesn't matter because we are going to ignore the negative sign. But if we don't know which number is bigger and which number is smaller, we need the absolute value function. So let's fill in the blanks here. M minus N is, without absolute value, the change from, now remember, the final value comes first, and the initial value comes second in the subtraction. So because m comes first, it's our final value, and n in the subtraction is second, is our initial value. It's the reverse in the second one. N minus m is the change from m to n. The final value is written first in the subtraction, and the initial value is written second. With absolute value, we're talking about the distance, and it's the distance between the two values. And so the word between is indicated by the subtraction in that statement. And so the first one, we have the distance between m and n. And in the second one, it's still distance, but it's between n and m. However, it doesn't really matter the order. Those two things are equal to each other. So in number 6, we have true for this statement because those two distances, whether we go from m to n or the other way around, they are equal. With distance, the direction doesn't matter. And so true because distance between m and n is the same as the distance between n and m. Now, in the second case, we have no absolute value, so we're talking about change here. And we have the fact that direction matters. We have a different initial and a different final value in both of these cases. So this is false because those two expressions will have opposite signs. One of them will be an increase, while the other one will be a decrease. which means that those values, whatever m minus n and n minus m work out to be, they will be negatives of each other. One positive, one negative, because one will be an increase going to the right, and the other will be a decrease going to the left by the same number of spaces. So the first one is true, and the second statement is false. So now let's take a look at two numbers, a and b, and we're told that a is greater than b. So on our number line, our greater numbers go to the right, and our smaller numbers go to the left. Now we want to rewrite each expression without using absolute value. We know that bigger minus smaller, so numbers that are more on the right minus numbers that are more on the left, will have a positive difference. And then smaller minus bigger will have a negative number for the difference. The first case is talking about the distance between a and b, and so we want distance not to be negative, so that will equal a minus b without the absolute value. Bigger minus smaller is positive. But that distance is the same as the distance in the second case, and so we have these two absolute value statements are equal, and the distance is the bigger number minus the smaller number still. Both of these distances will be positive. Now let's take a look at some actual number examples. In part A of number 8, the absolute value of negative 12 is just equal to 12. But we want to think of this in terms of the geometric interpretation. So we can see that negative 12 is really 0 minus 12. And now we are looking at the distance between 0 and 12 on a number line. And that number of spaces is 12. We get that distance by taking the bigger number minus the smaller number, 12 minus 0. So that one might be a bit more straightforward than the next. Here we have some square root numbers, and if we plot the two numbers on a number line, the square root of 2 is smaller than the square root of 3, so it goes to the left, and the square root of 3 goes to the right. Because we have absolute value in this statement, we're looking for distance. And to come up with the distance, we want a non-negative answer. So we take the bigger number minus the smaller number to get a positive result. The square root of 3 is bigger than the square root of 2, and so our bigger minus smaller positive distance answer will equal the square root of 3 minus the square root of 2 without absolute values. The next case involves absolute values, so it's still distance, and it's still the same two numbers on the number line, and so our bigger number minus our smaller number will give us a positive answer. But in B and C, those are the same two distances because it doesn't matter whether we go from left to right or right to left when we calculate distance. We're looking at the number of spaces in between. We're not looking at an increase or a decrease as we would with change. So our absolute value of that is our distance, which is the square root of 3 minus the square root of 2. In part D, we know that pi is approximately 3.14, which is a bigger number than 1. And so we can see that we have the absolute value of a bigger number minus a smaller number. We can plot those on a number line. 1 goes to the left, and pi goes to the right. And so our distance is going to be a positive answer, which is the bigger number minus the smaller number without absolute values. And so the absolute value of pi minus 1 exactly equals pi minus 1. And for the last example in part E, we have the same absolute value of 1 minus pi, which is still talking about the distance between 1 and pi, which is still going to be a positive answer. And in this case, it's the same as the absolute value of pi minus 1, which is just pi minus 1. Remember, we're taking the bigger number minus the smaller number to get a positive answer. In number 9, then, we have an equation, and we are told the absolute value of x minus 3, and it is written out in words. We see that the absolute value here is what we read as distance. And then the word between comes from the subtraction in between the two numbers. So we right now have the distance between and then an is coming from the equal sign. So with these words as anchors, we can fill in the blanks. The distance between x and 3 is 5 spaces. Now we can rewrite that, rearrange it to say x is 5 spaces away from 3. When we have this, we can think about what kind of shape has a constant distance away from something. And we have a circle with a constant radius away from the center. And so we have a radius of 5 and a center of 3 on the x-axis. The reason we're on the x-axis is because we have an x variable. And so x is going to be the intersection of the circle and the x-axis, and there are 2 points, one to the left of the center and one to the right. The one that is to the right of the center is starting at 3 and increasing by the radius of 5, which takes us to an x-coordinate of 8. We could also go to the left of the center on the x-axis. In this case, if we start at 3 and go to the left 5 spaces, we go 3 minus 5, which takes us to an x-coordinate of -2. So we can see that there are 2 solutions or values for x which convey this information. And that's how we use the circle to solve the absolute value equation, to say that x is either equal to -2 or +8. We use the word or in between here because x can't be both -2 and 8 at the same time. Now we can use the same strategy for filling in the blanks with an inequality statement. Again, we have the absolute value, which means the distance. And so I will color code this here with red. And then the word between comes from the subtraction in between the values of x and 3. And so we have the distance between x and 3 is less than 5 spaces. So instead of having an equality, which was exactly 5 spaces, we're now talking about being less than 5 spaces away from the center. So now we're not interested in being on the circle, which was a point that was exactly 5 spaces away. Rather, we want to be less than 5 spaces away. So we don't want to be at x equals -2 or 8, but rather we want to be inside the circle because all of those points represent x values that are closer to the center than being 5 spaces away. So with the less than statement, we want to be inside the circle. And we can write our answer using interval notation by saying that x is any value on the green line in between the boundary points of -2 and 8. So we say that x is contained from -2 on the left to 8 on the right. But we use these round brackets to indicate that x does not equal those end values. We use the Greek letter epsilon, which tells us that x is a member of the set of values. This is a set notation variable that we will use a lot. And so x is a member of the set of x values from -2 on the left to 8 on the right. We could also write this set of values using an inequality notation. And we are going to say that we have -2 on the left, x is in the middle, and 8 is on the right. So when we set up our values from smaller to larger, going from left to right, we always use an inequality symbol that opens up to the right-hand side. That's because our numbers keep increasing as we go from left to right. Now we can take this same strategy and apply it to the third statement, which is another inequality. And here we see that the absolute value of x minus 3, still the absolute value means distance, and still subtraction means between. And we have between x and 3, now in this case, is more than 5 spaces. So to be exactly equal to 5 spaces away meant to be on the circle, to be less than 5 spaces away meant to be inside the circle, and to be more than 5 spaces away means that our x values are outside the circle. But still on the x-axis, so we exclude the end values of -2 and 8, but x is outside the circle. And so x is any of those values in green, and we can use interval and inequality notation to write our sets. For the interval notation, x will be between -∞ and -2 on the left. So we use x epsilon -∞ to -2, and then we have a gap before the next set of x values. So we use the union symbol or the word or. We use union for interval notation, and then we know that x will be between 8 and infinity on the right-hand side. For the inequality notation, we use the word or, and we don't use negative infinity. We simply say that x is to the left of negative 2. Then we have the gap, so we use the word or instead of the union symbol. And then we have 8 and then x to the right. So we are lining up our values and variables from left to right so that the values are increasing, and we always open our inequality symbol to the right. So we can either use interval or inequality notation to state our answers. In number 10, we have variations on the same theme. So for each question, we will write a verbal statement and then the picture to accompany the geometric interpretation. So for parts A, B, and C, we have the same absolute value of x minus 4 and then a 7. The first one, part A, says we have the distance between x and 4, which is equal to 7. And so here, I'm just emphasizing the between part comes with the subtraction between the x and the 4. I also like to emphasize that the 7 means 7 spaces, as that reminds me that the 7 is the distance. We can rearrange this sentence to say that x is exactly 7 spaces away from 4. It's also true that 4 is exactly 7 spaces away from x, but x is the variable that we want to isolate, so when we write x is, we see x equals. So 7 is the radius of the circle, and 4 is the center. So we draw the x-axis. We draw a circle of radius 7 centered at 4. Now we know that x has to be the intersection of the circle and the x-axis, and we see that there are 2 intersection points for x to be exactly on the circle and on the x-axis. To get to the rightmost x value, we start at 4 and we increase by the radius, so 4 plus 7 takes us to the right x coordinate of 11. We can also decrease from 4 by the amount of 7, which takes us to the x coordinate on the left of negative 3. So our solution here says that x is either equal to negative 3 or 11. Now the word or is really important here because x can't be both negative 3 and 11 at the same time. As part of our communication of our thinking and our logic and reasoning, we will use the right word. In this case, it's or. In part B, we have a slight variation on the first question, and we have a less than symbol instead of a pure equal to, and we also have an equal to. So now we write that the distance between x and 4 is less than or equal to 7 spaces. We change the picture slightly. We still have the x-axis, we still have a circle with a center of 4 and a radius of 7. We still have the boundary points, the ends of the circle at negative 3 or 11. But in this case, we also want x to be less than 7 spaces away from 4. So x could be 1 space to the right of 4, or 3 spaces to the left of 4, for example, as long as x is not more than 7 spaces away from the center. So here we have that x could be any of the x values in between negative 3 and 11, as well as on those 2 endpoints. So our solution in inequality notation says that negative 3 is less than or equal to x, which is less than or equal to 11. And in the last part, part C, we've replaced the inequality symbol this time with a greater than symbol. So instead of less than or equal to, we have purely more than or greater than. So in this case, on our circle, the same radius, the same center, the same x-axis boundary points, but instead of being on the circle or inside the circle, the x values that we want will be outside the circle. We want to be more than 7 spaces away from the center. So we still have our 2 left and right x boundary points, and this time our solution is going to be to the right of 11 or to the left of negative 3. I use open circles at the boundary values to exclude them. If we had an equal to in the inequality statement, we would close those to include them. So we have x is to the left of negative 3 or to the right of 11. So I'm going to write my values in order from left to right. I first put an x, then I write negative 3, and then there's a gap in the graph that I will write an or, which is union in the interval notation, and then 11, and then x. And because we are increasing our values on the number line as we go from left to right, our inequality symbol will always open to the right. So we say x is less than -3 or 11 is less than x. We'll take a look at the next three as a set again because they involve the same numbers of 3 and 9. When we take a look at part D, the absolute value of x plus 3 equal to 9 could be translated into words, which helps us to draw our geometric picture. And it says the distance, because of absolute value, between, because of the subtraction sign. But here we don't actually have a subtraction sign. And so we need to make sure that when we interpret this verbally, the absolute value inequality or equation has a subtraction. So we are going to subtract a -3, which turns into the x plus 3 that we had to start with. And now we can see the distance between the two values of x and -3. So we actually have to pull that plus 3 apart. And the first subtraction sign is how we read the word between. The second subtraction or negative sign belongs to the 3, which is our center value of -3, and we have a radius of 9. So we finish off the distance between x and -3 exactly is 9 spaces. So from here we can draw our number line and we can sketch our circle. We have the x-axis, a circle of radius 9, centered at -3 along the x-axis. Because we are exactly equal to 9 spaces away from the center, we want to be exactly at the intersection of the circle and the x-axis. So the right end point will be -3 increased by the radius of 9, which takes us to 6. And the left x boundary value will be starting at -3 and decreasing by the distance of 9. So -3 minus 9, which takes us to an x value of -12. We can write our solution then as x either equals -12 or 6. And I see that I've written -6 there. I will change it later on. So now we're going to look at the next part E, which has the same center and the same radius, but this time we are talking about being more than 9 spaces away from the center. We're no longer interested in being on the circle, but rather we want to be outside the circle. So we have the same boundary values, but we want to be to the right of 6, not including 6, or we want to be to the left of -12, not including -12. If we use inequality notation, I'll just write it to the left of the question here, we know that x is either to the left of -12, so x will be less than -12. There's a gap, so I write the word or, and then 6 is to the left of x. So we always put our numbers increasing from left to right, meaning that our inequality symbol opens to the right. And so between x and -12 we have a less than, and between 6 and x we have a less than, and then we have the word or in between the two sets. Now for part F we see that we have a less than symbol, so we are going to be looking at the distance between x and -3 is less than 9 spaces. We're still not including the endpoints, but now we're looking in between the two boundary points. We're looking inside the circle for our x values. We exclude the endpoints, and we want to make sure that all of the x values in between are included. So I only need to write x one time in this interval notation or inequality notation. So I have -12, then x, and then 6. I'll just fix this 6 now to say +6 instead of -6. So from left to right, -12 comes first, then x, then 6. I open my inequality symbol to the right. And that's the solution for part F. Now the last three questions are all a little bit different from one another, so we'll take them one at a time. In part G it says the absolute value of x is greater than or equal to 10, but we didn't have a subtraction, so we can rewrite x as x minus 0. And that allows us to see the distance between x and 0, which is greater than or equal to 10. So we need that subtraction inside the absolute value statement to be able to see the between. We can rewrite that or restate this to say that x is 10 or more spaces from 0. So we have a center of the circle on the x-axis at 0, we have a radius of 10, and x is going to be any value that lies on the circle or beyond the circle on the x-axis. So if we want to get our right x endpoint, we start at 0 and increase by 10. To get our left x boundary point, we start at 0 and get to negative 10. And then we want to include those values as well as going beyond the circle. So x is going to be one of two different sets, and there's a gap in the graph, so we will use the word or. We have x for every point in red, and increasing our numbers from left to right, we see an x, then a negative 10, then the gap, then 10, then x. We just write those in order from left to right. When we do that, we can put the or in the middle, and we're going from left to right, which means our inequality symbol will open up towards the right. That ensures that smaller numbers are on the left and bigger numbers are on the right. Putting the or in the middle ensures that x can't be both on the left-hand set and the right-hand set at the same time. We could also rewrite 10 less than x as x greater than 10, but I really like putting my numbers and my variables in order from left to right, from smallest to largest. In part H, we can interpret this one. We do have a subtraction, so it says the distance between x and 8 is negative 3 spaces. And of course, this is a problem because we can't have a distance that is negative. So the distance between x and 8 is negative 3. Well, this is an impossible statement. So keeping in mind what the meaning of these things means allows us to solve just by logic. So knowing that a distance of negative 3 is impossible means that we have no solution to this equation. We know that the distance can't be negative, the distance can be positive, the distance can also be 0. So we say that x is contained in the empty set, and we use this symbol to represent the empty set. It's just a mathematical way of saying there is no solution. There is no value of x that will make that green inequality a true statement. Okay, the last question is part I, and it's a little bit different still, so we'll take another look at it on a full slide. It says the absolute value of 3x minus 12 equal to 5, which we can interpret verbally. I encourage writing it verbally first and then using that to come up with a geometric interpretation. So let's just think about what this says. The absolute value says distance, the subtraction says between, and we need to find between what two things. So something and something. We have a straight equation, so the word is applies, and we have 5 spaces. So we are talking about the distance between 3x and 12 being 5 spaces. We could also say that 3x is 5 spaces away from 12. So instead of being on an x-axis, we are now on a 3x axis. Now we have a center of 12 and the radius of the circle is 5. So even if we're not sure what to do with that 3x, let's just go through some of the same steps we'd seen before. We can interpret our boundary points starting at 12 and increasing by 5 to get to the right boundary point. We have a value of 12 plus 5, which is 17. And then starting at 12 and decreasing by 5, we get 12 minus 5, which is 7. So these are two boundary points, and they are values not for x, but in this case for 3x. So we can now state that our solution so far says 3x equals 7 or 3x equals 17. And when we solve for x, we divide both sides of each equation by 3, and now we have the x that we wanted to solve at the beginning. We know we wanted to solve for x because the question says to solve for x. So we end up getting that x is either equal to 7 over 3 or x is equal to 17 over 3. So having this same strategy allows us to take a bit of a less routine problem, something unfamiliar, and still solve it. Okay, now we're going to take a look at Desmos to compare some expressions. We've got 4 different functions or expressions here, and we're trying to see if any of them are equal to one another. So let's go to Desmos and plot all of these different expressions or graphs. The first one says the square root of x squared, whereas the second one says the square of the square root of x. Those two graphs are different. When we turn on the third one in green, it looks different again. We can just turn a few off and play around and make sure that we're not seeing any overlapping. And we turn them all off and take a look at the last one. We compare these last two. They look the same, but in fact the blue one is only half a graph. But the first one and the last one, those two are identical. And so we're just using technology to help us see that the red expression and the black expression are identical. And so we come up with something that is an identity. The square root of x squared and the absolute value of x are identical expressions. They're written differently, but they are interchangeable, or we can substitute one expression for the other. Now we might think that the square root and the square cancel, leaving us with x, but the graph told us that that wasn't the case. These two expressions are equivalent and interchangeable. So in part 12, or number 12, we see that the square root of x squared will have the graph of y equals the absolute value of x, which is c. So we just want to kind of remind and commit to memory that basic identity. And we can use it in number 13 when we're solving the square root of x squared greater than 5. We can replace the square root of x squared with what it is identical to. Namely, we can replace the square root of x squared with the absolute value of x. And now we can replace x with x minus 0 so that we can think verbally. And we get that the distance between x and 0 is more than 5 spaces. So we have an x-axis intersecting with the circle, centered at 0 along the x-axis with a radius of 5. And the inequality is saying that we want to be outside the circle along the x-axis. So the first thing we do is find the two boundary values. We will have a right boundary value at 0 plus 5, and then the left boundary value of 0 minus 5. X is not meant to be exactly 5 spaces away, so we exclude those boundary values of 5 or negative 5. And so we can then interpret our solution as an inequality or an interval notation. And here I'll use inequality notation to say that x is going to be to the left of negative 5, so x is less than negative 5, or 5 is less than to the left of x. We've now taken a look at absolute value and one-dimensional distance from a conceptual and a geometric point of view. So we will be able to continue on looking at rectangular coordinates and two-dimensional distance. We're going to make more connections between lines, slopes, Pythagorean theorem, distance formula, and circles as we continue working on this rectangular coordinates lesson. Thanks for making it this far, and stay tuned for more interesting connections.